Friends, welcome back. In the last few videos, we've been discussing the steps in a training loop in PyTorch, and there's a fair bit going on. So in this video, we're going to step back through what we've done just to recap, and then we're going to get into testing. And it's nice and early where I am right now. The sun's about to come up. It's a very, very beautiful morning to be writing code. So let's jump in. We've got a little song here for what we're doing in the training steps. For an epoch in a range, call model.train, do the forward pass, calculate the loss, optimize a zero grad, loss backward, optimize a step, step, step. That's the little jingle I use to remember the steps in here, because the first time you write it, there's a fair bit going on. But subsequent steps and subsequent times that you do write it, you'll start to memorize this, and even better, later on, we're going to put it into a function so that we can just call it over and over and over and over again. With that being said, let's jump in to a colorful slide, because that's a lot of code on the page. Let's add some color to it, understand what's happening. That way you can refer to this and go, I see what's going on now. So for the loop, this is why it's called a training loop. We step through a number of epochs. One epoch is a single forward pass through the data. So pass the data through the model for a number of epochs. Epochs is a hyperparameter, which means you could set it to 100, you could set it to 1,000, you could set it to 1, as we're going to see later on in this video. We skip this step with the colors, but we put the model in, we call model.train. This is the default mode that the model is in. Essentially, it sets up a whole bunch of settings behind the scenes in our model parameters so that they can track the gradients and do a whole bunch of learning behind the scenes with these functions down here. PyTorch does a lot of this for us. So the next step is the forward pass. We perform a forward pass on the training data in the training loop. This is an important note. In the training loop is where the model learns patterns on the training data. Whereas in the testing loop, we haven't got to that yet, is where we evaluate the patterns that our model has learned, or the parameters that our model has learned on unseen data. So we pass the data through the model. This will perform the forward method located within the model object. So because we created a model object, you can actually call your models whatever you want, but it's good practice you'll often see it just called model. And if you remember, we'll go back to the code. We created a forward method in our model up here, which is this. Because our linear regression model class subclasses nn.module, we need to create our own custom forward method. So that's why it's called a forward pass, is because not only does it, well, the technical term is forward propagation. So if we have a look at a neural network picture, forward propagation just means going through the network from the input to the output. There's a thing called back propagation, which we're going to discuss in a second, which happens when we call loss.backward, which is going backward through the model. But let's return to our colorful slide. We've done the forward pass. Call a forward method, which performs some calculation on the data we pass in. Next is we calculate the loss value, how wrong the model's predictions are. And this will depend on what loss function you use, what kind of predictions your model is outputting, and what kind of true values you have. But that's what we're doing. Here we're comparing our model's predictions on the training data to what they should ideally be. And these will be the training labels. The next step, we zero the optimizer gradients. So why do we do this? Well, it's a little confusing for the first epoch in the loop, but as we get down to optimizer.step here, the gradients that the optimizer calculates accumulate over time, so that for each epoch, for each loop step, we want them to go back to 0. And now the exact reason behind why the optimizer accumulates gradients is buried somewhere within the PyTorch documentation. I'm not sure of the exact reason. From memory, it's because of compute optimization. It just adds them up in case you wanted to know what they were. But if you find out exactly, I'd love to know. Next step is to perform back propagation on the loss function. That's what we're calling loss.backward. Now, backpropagation is we compute the gradient of every parameter with requires grad equals true. And if you recall, we go back to our code, we've set requires grad equals true for our parameters. Now, the reason we've set requires grad equals true is not only so backpropagation can be performed on it, but let me show you what the gradients look like. So let's go loss function curve. That's a good idea. So we're looking for some sort of convex curve here. There we go, L2 loss. We're using L1 loss at the moment. Is there a better one here? All we need is just a nice looking curve. Here we go. So this is why we keep track of the gradients. Behind the scenes, PyTorch is going to create some sort of curve for all of our parameters that looks like this. Now, this is just a 2D plot. So the reason why we're just using an example from Google Images is one, because you're going to spend a lot of your time Googling different things. And two, in practice, when you have your own custom neural networks, right now we only have 2 parameters. So it's quite easy to visualize a loss function curve like this. But when you have, say, 10 million parameters, you basically can't visualize what's going on. And so PyTorch, again, will take care of these things behind the scenes. But what it's doing is when we say requires grad, PyTorch is going to track the gradients of each of our parameters. And so what we're trying to do here with backpropagation and subsequently gradient descent is calculate where the lowest point is. Because this is a loss function, this is MSE loss, we could trade this out to be MAE loss in our case, or L1 loss for our specific problem. But this is some sort of parameter, and we calculate the gradients because what is the gradient? Let's have a look. What is a gradient? A gradient is an inclined part of a road or railway. No, we want it in machine learning. What's it going to give us? In machine learning, a gradient is a derivative of a function that has more than one input variable. Okay, let's dive in a little deeper. See, here's some beautiful loss landscapes. We're trying to get to the bottom of here. This is what gradient descent is all about. So, oh, there we go. So this is a cost function, which is also a loss function. We start with a random initial variable. What have we done? We've started with a random initial variable. Right, okay, and then we take a learning step. Beautiful. This is W, so this could be our weight parameter. Okay, we're connecting the dots here. This is exciting. We've got a lot of tabs here, but that's all right. We'll bring this all together in a second. And what we're trying to do is come to the minimum. Now, why do we need to calculate the gradients? Well, the gradient is what? Oh, value of weight. Here we go. This is even better. I love Google Images. So this is our loss, and this is the value of a weight. So we calculate the gradients. Why? Because the gradient is the slope of a line, or the steepness. And so if we calculate the gradient here, and we find that it's really steep, right up the top of this incline, we might head in the opposite direction to that gradient. That's what gradient descent is. And so if we go down here, now what are these step points? There's a little thing that I wrote down in the last video, at the end of the last video, I haven't told you about yet, but I was waiting for a moment like this. And if you recall, I said kind of all of these 3 steps, optimize a zero grad, loss backward, optimize a step, are all together. So we calculate the gradients because we want to head in the opposite direction of that gradient to get to a gradient value of 0. And if we get to a gradient value of 0 with a loss function, well then the loss is also 0. So that's why we keep track of the gradient with requires grad equals true. And again, PyTorch does a lot of this behind the scenes. And if you want to dig more into what's going on here, I'm going to show you some extra resources for backpropagation, which is calculating this gradient curve here, and gradient descent, which is finding the bottom of it towards the end of this video. And again, if we started over this side, we would just go in the opposite direction of this. So maybe this is a positive gradient here, and we just go in the opposite direction here. We want to get to the bottom. That is the main point of gradient descent. And so if we come back, I said, just keep this step size in mind here. If we come back to where we created our loss function and optimizer, I put a little tidbit here for the optimizer because we've written a lot of code and we haven't really discussed what's going on, but I like to do things on the fly as we need them. So inside our optimizer, we'll have main 2 parameters, which is params. So the model parameters you'd like to optimize, params equals model 0.parameters in our case. And PyTorch is going to create something similar to this curve, not visually, but just mathematically behind the scenes for every parameter. Now, this is a value of weight, so this would just be potentially the weight parameter of our network. But again, if you have 10 million parameters, there's no way you could just create all of these curves yourself. That's the beauty of PyTorch. It's doing this behind the scenes through a mechanism called Torch AutoGrad, which is auto gradient calculation. And there's beautiful documentation on this. If you'd like to read more on how it works, please go through that. But essentially behind the scenes, it's doing a lot of this for us for each parameter. That's the optimizer. Then within the optimizer, once we've told it what parameters to optimize, we have the learning rate. So the learning rate is another hyperparameter that defines how big or small the optimizer changes the parameters with each step. So a small learning rate results in small changes, whereas a large learning rate is in large changes. And so if we look at this curve here, we might at the beginning start with large steps so we can get closer and closer to the bottom. But then as we get closer and closer to the bottom, to prevent stepping over to this side of the curve, we might do smaller and smaller steps. And the optimizer in PyTorch, there are optimizers that do that for us, but there is also another concept called learning rate scheduling, which is, again, something if you would like to look up and do more. But learning rate scheduling essentially says, hey, maybe start with some big steps, and then as we get closer and closer to the bottom, reduce how big the steps are that we take. Because if you've ever seen a coin at back of couch, this is my favorite analogy for this. If you've ever tried to reach a coin at the back of a couch, like this excited young chap, if you're reaching towards the back of the couch, you take quite big steps as you, say your arm was over here, you would take quite big steps until you get to about here, and then the closer you get to the coin, the smaller and smaller your steps are. Otherwise, what's going to happen? The coin's going to be lost, or if you took 2 small steps, you'd never get to the coin. It would take forever to get there. So that's the concept of the learning rate. If you take 2 big steps, you're going to just end up over here. If you take 2 small steps, it's going to take you forever to get to the bottom here. And this bottom point is called convergence. That's another term you're going to come across. I know I'm throwing a lot of different terms at you, but that's the whole concept of the learning rate. How big is your step down here in gradient descent? Gradient descent is this. Backpropagation is calculating these derivative curves or the gradient curves for each of the parameters in our model. So let's get out of here. We'll go back to our training steps. Where were we? I think we're up to backpropagation. Have we done backward? Yes. So the backpropagation is where we do the backward step. So the forward pass, forward propagation, go from input to output. Backpropagation, we take the gradients of the loss function with respect to each parameter in our model by going backwards. That's what happens when we call loss.backward. PyTorch does that for us behind the scenes. And then finally, step number 5 is step the optimizer. We've kind of discussed that. As I said, if we take a step, let's get our loss curve back up. Loss function curve, doesn't really matter what curve we use. The optimizer step is taking a step this way to try and optimize the parameters so that we can get down to the bottom here. And I also just noted here that you can turn all of this into a function, so we don't necessarily have to remember to write these every single time. The ordering of this, you'll want to do the forward pass first, and then calculate the loss, because you can't calculate the loss unless you do the forward pass. I like this ordering here of these 3 as well, but you also want to do the optimizer step after the loss backward. So this is my favorite ordering. It works. If you like this ordering, you can take that as well. With that being said, I think this video has gotten long enough. In the next video, I'd like to step through this training loop 1 epoch at a time so that we can see. I know I've just thrown a lot of words at you that this optimizer is going to try and optimize our parameters each step, but let's see that in action, how our parameters of our model actually change every time we go through each one of these steps. So I'll see you in the next video. Let's step through our model.